Okay, and this is Ahmed's last talk, wrapping up the solution of the current understanding, which has gone a long way to solving the black hole information paradox. But we're going to hear a more interesting variation of the SYK model that perhaps will enable us to understand the bulk gravitational theory much better. And are there any questions about school timetable or anything? Okay. So Ahmed.
Thanks. Okay, thanks a lot, David. Okay, let me just quickly recap what we covered last time. We were interested, oh, these TVs are not on.
Yeah.
Should,
It's okay.
sure? Well, why not? Oh, okay, that's a good one. Okay. We were interested in computing the von Neumann entropy of the two bath regions that keeps track of the entropy of the radiation that is emitted by the black hole, and using the standard formula for entanglement entropy, namely just the von Neumann entropy of just the matter in the bath regions, we found the behavior that the entropy just grows with all time, and we talked about the issues with that. Then I introduced this new formula. Well, it's not really new. It appeared in the past in the context of ADS-CFT, and also even before that by Jacob Bekenstein, where he defined the generalized entropy and so on. And the claim was that we have to use a version of that formula here to capture the true entropy of the Hawking radiation. Okay? And this new entropy, this function of the generalized entropy, it contains extra contributions, which you might describe as geometric contributions, the area of some boundary of some region in the bulk. What comes with that is also a modification of which subregion you're meant to compute the standard von Neumann entropy of the matter on. I gave you guys that formula, and I showed you that it gives nice results. In particular, if you say that the entropy of the radiation is given by the minimum between the Hawking's original answer, which we right now will call the trivial surface contribution, and the contribution coming from the island, which is somewhere inside the black hole, and you take the minimum between these two, you reproduce the page curve.
Can you recall it again? What is the definition of the trivial surface and of the island generically?
Good. The trivial surface here just means that it's where there are no islands, or rather there are no, remember we said that we can add x's, that is, you can add region sigma in the bulk, such that x is homologous to the intersection of Q with the boundary. Okay. Or maybe let me say it slightly differently. Let me come to your question in a second. Okay? First, this is an observation that this formula gives the right answer. Why am I calling a trivial surface an island? Okay. That's going to become clear when we carefully define what we mean by the entropy of the region Q in the bath. The way you should do that is by, a careful way of computing the entropy is by the replica trick, which involves considering n copies of your system, then acting with the derivative of n, and then taking n goes to 1. when you consider n copies of the system, you get, so here's the branch cover. There are n copies here branched across this. And you are meant to consider all possible ways of filling in the gravitational region. Okay, so in principle here, there's an integral over the metric, which includes summing over all possible manifolds with these circles. There are n of these circles as sort of boundary conditions. And there are many ways of doing that. One way is the trivial way, meaning that each circle, there are n of them, but each circle is a separate disk. Okay? That is what I mean by the trivial surface. In this context, when each circle has its own disk, the only branch cuts that appear are the ones outside in the Bath region, namely where the original Q was. Okay, that's this thing. So that's what I mean by the trivial surface, in that there's no extra branch cut that appears in the gravity region. But there are more contributions. One contribution is, or another one, is where you create, where you have a branch cut inside the gravity region. Okay? For the case, just to picture what that means, for the case of n equals 3, it looks something like this. You have this three-mouthed wormhole that connects the three circles together. Notice that this configuration is symmetric about the three copies, and so this is called a replica symmetric contribution. There are other contributions that are not replica symmetric, which in principle you should include. So for example, you can have a wormhole connecting these two. Oops, that looks weird. Here's a wormhole, while this guy is a disk. This is a non-replica symmetric configuration, and there are two more. What those contributions do is that they eventually just smoothen out the page growth. They're not really important at the beginning, and they're not important at the end, but they are important around the page time. So I'm just going to ignore those. And okay, so then how do we get the formula that we like from this discussion? Well, here, what happens, we're looking at the saddle point contributions to Zn, and so then so you're summing over saddles, where n here is now very close to 1. You find that in the exponent, the on-shell action is just going to be given by this, which is just a generalized entropy. Implicitly here, one of these saddles is this one, and hence there's no area term. Okay? There's no area term, and there's no branch cut in the center. Okay? You should, that's included in the sum. And so there's now competition between different terms of the sum, and the one that wins is the one that has minimal argument in the exponent, namely minimal generalized entropy. This object here is a generalized entropy. Okay, so we have competition. So the competition between the saddles gives you the minimality condition. And the extremality condition comes from the fact that these are meant to be on-shell solutions or on-shell evaluations of the action, which means that as you vary the parameters A, you have to get 0. Remember, A is a parameter in the gravity region. It tells you where these locations are. It's a property of the wormhole. It determines the geometry of the wormhole. And since we're only looking at a saddle point contribution, it must be the case that this is 0. Any questions?
Who is the leading loser?
The leading loser.
Yeah.
The
Who is
next
who-
the next
Yeah,
card.
but that depends on where you are. So, I see. I actually don't know. If I was to guess, I would say that here, so the leading answer is the trivial surface. Then I think the replica non-symmetric contributions are most likely larger than the fully replica symmetric contribution. That's my guess, but I haven't actually checked that.
Why this extra branch cut is, on this inside the branch region should not, we are considering only Q as the origin. Then why this extra branch?
So the Q is the original branch cut that you've introduced by hand because you want to compute the entropy of that region. Then there's an extra branch cut that is created, basically just to represent this wormhole. So what does a branch cut do? It says that if I go through it, I will emerge on the other sheet. Let's try that here. So I'm going into the gravity region. Here, I went into the gravity region. Oh, snap, I'm in the other sheet. Okay, that's the branch cut is supposed to represent the wormhole. Yeah?
So for every finite time, the drawing on top is almost correct because you have a discontinuity in the metric or?
Do you have a discontinuity in the metric
Why did this,
when you go through this way?
yeah.
No.
No, I mean not to the other sheet.
Um,
I mean, why this is not trace correlation function for finite time?
Good. Because, so, for finite n, okay, let me see your question again. So I made a comment last time that when n is an integer, you shouldn't think of these as twist operators. You should think of only these as twist operators. Why? Because the space-time here really is, it has a conical singularity. Okay? Here, when n is finite, there's no conical singularity. This wormhole is perfectly smooth.
After you,
Yeah, but when n is an integer, it's perfectly smooth. There's no singularity. But when you take n close to 1, then now you actually do have a singularity.
What kind of
You have a conical excess. It's basically just a semi-classical answer. The semi-classical, it's like this guy, pure just standard AES 2, but with a small conical excess here and here.
Is the contribution from, say, the higher and higher ended wormholes, does it fall in any obvious way, the contribution is there?
I mean, the only obvious thing I can tell you is everything else depends on the details of the size of the wormhole and so on and so forth. But the most important factor is the phi naught factor. And that's what I have here. So it just goes as e to the minus 1 minus, sorry, plus 1 minus n phi naught over 4g Newton. So higher and higher topology are suppressed more and more and more.
About the connection between different copies, the connections are just along the branch cut, right? Not along the whole ADS disk.
So when n is an integer, the picture is like this. So if I go through and continue going, I'll emerge on the other side.
And if I focus on one replica, it's just
So I'm focusing on this region, say? Like that, you mean?
and no, actually on the actual sheet, then I have to go through the branch cut to transition, or just from anywhere in this taken.
Yeah, it doesn't matter where you are. So when let's say so n is an integer, then it doesn't matter which direction you go, so long as you aim yourself to go into the wormhole, you'll always come out on another sheet. So if I do this, I'll come out there. If I do that, I'll come out there. There's no it's hard to miss. It's hard for you to come back to the same sheet. Like the only way is to go straight through here and go around this way and come back. I don't know if that addressed the question. Yeah, Kobe.
So the structure follows from the fact that you decided to do this replica trick. I mean, you won't see these wormholes and you have another way to do it. So there is no other way to calculate an entropy or generalized entropy for, I don't know, simplified system, toy model. But it seems that it all comes from this replica trick.
Correct, yeah. I don't know of a way to do it with a single copy of the theory. It's kind of related to the fact that we don't know how to write down the density matrix, as in the matrix elements of the density matrix. Somehow gravity gives you the right tools to compute traces of the density matrix, but not the matrix itself.
So in the picture, so each time you have an X, it's another wormhole. I mean, if it was n equals 4, how would the crash, the squat? No, not this.
Oh, the Schwarzschild. Oh, yeah. This doesn't care about what the value of n is. Just as the angle. Yeah. Yeah.
At the page time, the contributions from the trivial surface and the island are equal. And so I would expect naively to get a factor of 2, but then there are the non-replica symmetric configurations to be described. How this factor of 2 comes to factor of 1
Yeah.
at the page time?
Yeah. It's like an order of limits kind of thing issue, but the more careful statement is that you should take into account the non-replica symmetric configurations, and that would break that degeneracy.
Can they come with negative signs
With negative signs.
with respect to this contribution?
Overall sign? No, I don't think so. Yep.
So actually, Amit asked a question last time. So if I understood him correctly, and also Kobe now, let's say we don't have a replica here. Is it correct in any way to think we have the black hole, it begins to radiate, and by some process somehow an island appears suddenly? Because there's no real evidence, because this happens in a replica way. Can we carry it to the single copy? This idea that it's somewhere behind the horizon, we should in some way find an island?
Yeah. Yes, in the sense that I briefly, at the very end of my talk yesterday, I talked about this example where if you have just one black hole, and you imagine you do an experiment on the Hawking radiation that involves another black hole, then you can amplify the probability that a wormhole goes from the new black hole into the old black hole.
Is it transversal?
It is not traversable, no, but it could be, but it doesn't have to be. But it's a wormhole that can change the state of the interior of the old black hole. I don't know if this is cheating, because in this example, I didn't have to consider many copies of the old black hole, but I introduced my own new black hole. I don't, but what you might say is, but okay, is there an operation on the radiation that you can do without involving a new black hole that can change the interior? I would say yes. It is those that are captured by introducing a new black hole that would change the interior. But yeah.
Question.
Yeah?
You mentioned that away from integer n, the solution before the orbifold is singular.
Yeah? Sorry. At non-integer n, it is singular, yes.
Before you take the orbifold. Is that right?
Before I take the orbifold. Yeah, it must be, I guess. Yeah, it has to be, I think, yeah.
Do you know if this also happens like in with Maldacena, simpler setups?
Yeah, I think it's the same thing. There you just, yes, I think it also happens there. Okay.
I have a next question. Like,
Yeah.
while we are considering the n equal to 3 for the other points, like we have to at the end of the day we have to take n tends to 1 limit.
Yes, yes, yes.
So while we
Oh, just so for pedagogy, just so you can
but they are not
picture an example.
contributing. Right.
Say that again? But
Those
they
n equal
are.
to 3, those n equal to 3 for they are not contributing to the calculation.
Well, we care about the n near 1, but in order to extract the n near 1 behavior, you need to, in principle, you need to evaluate it for all n, and then find the right analytic continuation that you can take down to n near 1, in principle. But by assuming replica symmetry and so on, it actually simplifies, and you don't actually have to do that. Okay, there are no more questions. I will change the subject. Okay. I will talk about double-scaled SYK and the emergence of a bulk Hilbert space. Before I do that, let's talk about JT gravity. Remember, JT gravity had, well, it has, the fields in JT gravity are the metric and the dilaton, okay? So that's 2 degrees of freedom. But it's a theory of gravity, and so it has constraints and diffeomorphism invariance. It has 2 constraints. Oh, sorry, not 2 degrees of freedom. What am I saying? It's 4, thank you. 4 degrees of freedom. Thank you. It has 2 constraints. Coming from the G0I equals, yeah, this is the Einstein tensor, G0I equals 0 for all r's. And it has 2, and you have diffeomorphism invariance, so 2 coordinate transformations that you can do. So we started with 4. We can remove 2 degrees of freedom from constraints, and we can remove 2 degrees of freedom from coordinate transformations. So we have no degrees of freedom. What the hell is going on? Okay, the freedom, the dynamical information in JT gravity comes from the shape of the boundary. Let me be precise. So you recall, IJT has a terminate which looks like phi of r plus 2, typical, I guess, which means that the space-time is ADS2. Okay? ADS2.
Why is it that when you use coordinate transformation, you don't get ghosts? In string theory, you do gauge fixing of the transformation. You have ghosts.
Well, I'm not gauge tracing. I'm just saying that I can remove degrees of freedom by coordinate transformation. Yeah.
No, but I would like to understand what's the difference between what we do in string theory and here? Why is it that you don't count these are very important?
Well, I think roughly speaking, you can think of it as there being 2 ghosts. So and ghosts account for removing 2 degrees of freedom. I think that's roughly the way to think about it. Okay, so the fact that I have ADS2, so if I have ADS2, it means I can choose the metric of my spacetime. Let me choose a gauge, and say that ds squared is equal to minus dt squared. Oh, sorry. Let me stick with Euclidean. Okay, just regular Poincare coordinates. This is some coordinate system. that covers the Poincare disk. Okay? All right. Also in the action is the boundary term, which was the integral of phi. There's a boundary value of the dilaton, which I'm assuming to be a constant, times extrinsic curvature minus 1 on the boundary of two-dimensional manifold. The only degree of the only degree of freedom in this theory is the choice for what the boundary of M2 is. The boundary of M2 is not this circle that I drew here. At this circle, this metric diverges. Okay. The boundary M2 is some arbitrary curve within this Poincare disk, at which you impose the following boundary conditions. You say that phi boundary goes as some phi r over epsilon. Epsilon goes to 0. Phi r is the renormalized value of phi, some constant finite number, over epsilon, so this thing diverges. And GUU, U is meant to denote the time along this wiggly curve, goes as 1 over epsilon squared. Okay. Given that this is what the metric looks like everywhere, you can actually find the location from these boundary conditions, find the location of the curve in terms of t and z. Namely, you'll find that z of u along the curve goes as epsilon times t prime. I don't know if it's t prime squared or t prime prime. I think just t prime of u. Where t prime is a derivative with respect to u. Okay? If you, this information is sufficient to evaluate what the extrinsic curvature is. And you find the following answer. There's a G Newton here with some numbers. You get minus phi r over 8 pi g times the integral du, Schwarzian derivative between t and u, which means that, the definition of this is t prime, double prime over t prime, prime minus 1/2 t double prime over t prime squared. Okay, good. Okay, so that's good. Next is you can compute the energy of okay, no. First, the only okay, the equation of motion of this action is actually just T u is equal to a constant. That's actually the equation of motion. This constant is, it denotes actually the energy as measured at infinity. Okay? So this is equal to the ADM energy, in fact. Okay?
Why do we expect phi to blow up at the moment?
We don't expect it, we're imposing it. Okay? Okay. If this is equal to a constant, you find that the trajectory, the solutions, are just circles. Okay, it's just a circle. Okay? And obviously, this object here, the Schwarzian derivative is invariant under acting with an SL2 transformation on T, okay? Taking T to AT plus B over CT plus D, where the, yeah, okay? That involves to taking the circle and moving it around within the unit disk. Also, you can, this C here, the value of this C, can be related to the behavior of the dilaton inside the bulk. So if you solve for the dilaton, you find that there's a minimum of the dilaton in the center of the circle, and that's the value of the dilaton at the horizon. Right? The center of the circle ultimately is going to be the bifurcation surface of the black hole if we continue this solution to Lorentzian time. So this thing is equal to something like phi h squared divided by phi I think 0.5 r. Okay. Okay, so why am I, okay, so this is what the energy is. I want to make the following observation, that if you take, let's say you take 2 points on this circle, and, or rather, let's, okay, let me draw it here. Now I'm only drawing the inside circle. Let's ignore the outside circle. If you, suppose I give you 2 points here and here, T1 and T2, and let's ask about the length of the geodesic that connects T1 and T2. Okay, so there's a length as a function of T1 and T2. Clearly, this thing is only going to be a function of the difference between T1 and T2. Okay? Because I can add a little bit to T2, and I can subtract a little bit from T1. I guess it depends on how they, okay, how are we measuring the growth of T1, T2? So I guess if T always grows in this direction, so then it has to be the difference between T1 and T2. So if I add to this T2 and I add to T1, the length of the geodesic will stay fixed. So this is really a function of T1 plus minus T2. Okay. This variable here, let's call it delta. Okay. You find that the length of a geodesic, of this geodesic, goes as 2 times the logarithm of cosine of phi h over phi r times delta divided by phi h. No, actually, I think this is phi b here.
Ahmed, this T1 is equal to the same as the T0, and K squared is equal to DT squared for this.
Is that better? Thank you, thank you, thank you. I'm confused about something in my notes. I forget if this is phi b or phi r. It's not going to matter too much. So this is what the length is. And so one can make the following observation. But if you take this as the length, then you find that the ADM energy is equal to, so ADM energy, let's define that as H. It's equal to L dot squared plus e to the minus L. Okay? And so you have the energy in JT gravity can be thought of as, well, it's given by a Liouville Hamiltonian. Okay? So it has L dot squared plus a usual Liouville potential terms. Okay, so that's a quick recap of JT gravity. Now I'm going to talk about SYK. Any quick questions about this? Okay. All right, so let me write down the SYK Hamiltonian. It's given by I to the Q over 2 as a sum from I, oh, sorry, not Q, P. P over 2 from I1 all the way to IP. J I1 IP times Majorana fermions, P of them. P Majorana, meaning they have the following algebra. Psi I psi j is equal to 2 delta ij. I'm going to define this combination of fermions with the following capital psi. Psi to the p with lower index I. This lower index I is meant to be a combination of all these indices I1 to IP. These coefficients here, these couplings, are drawn from a Gaussian distribution where that satisfies the following formula, or the following variance. So they have zero mean, and the variance is given by the following. Some constant divided by lambda and choose q, where lambda is equal to 2 p squared over n. Yeah, okay, so that's the model. Any questions about this? Okay, so okay. So in this theory,
Strictly speaking, you need an anti-symmetrization.
Anti-symmetrization where? Oh, here with the size? With the size?
The J's are totally symmetric with the right-hand side.
Oh, yes. That's right. Let's, we can just choose to work with the convention that I1 is less than I2 is less than and so on and so on. Thank you. Okay. Suppose you're interested in computing the partition function. So Z is equal to trace, Hilbert space trace of the fermions, e to the minus beta h, where h is SYKH. This thing is a horrible thing to compute. Anything about it is horrible, unless you also average over J. Okay. Once you declare that your J is a random number with this distribution, this is a lot easier to compute.
Q is what? The small q.
Say that again? 2?
The q. Yeah.
Q is equal to P.
Sorry, can you repeat what is capital N?
Oh my god, yeah, sorry. Thank you. N is the number of fermions.
Again, and strictly speaking, we want the free energy quench.
No. So what do you mean? This is often what we like to talk about.
I know.
Yes.
But the thing that one starts with is the sort of the average of the couplings of the energy.
You mean specifically for the double scaled system, or you mean for the double scaled case, or do you mean in general?
In general.
Sorry, you're saying that we usually do this?
No. There's a system of this sort of couplings, but on averages over the ensemble of couplings, on averages the free energy, on averages observable, which are modestly. So this is self-evident system, so.
Well, it depends on what you compute.
This is like saying there's a dynamical thing on the trivial electron, as opposed to quench.
But for example, you might be interested in computing something like trace e to the minus beta h, trace e to the minus beta h. Question is now, where do you put the averaging? Are you going to average this multiplied by the average of that, or are you going to do something like this? This would give you a qualitatively different answer. Okay. So far, I didn't tell you, well, I didn't say what the scaling is in the double scaling. So this model is analyzed usually in the n goes to infinity limit. So you have an infinite number of fermions. And also in the p goes to infinity limit. Okay? It simplifies drastically when you do this. It simplifies in a different direction. If you take those two parameters to infinity, but keep lambda fixed. This is the so-called double scaling limit. DSSYK. Okay. And now we'll see what makes it so interesting.
Is it crucial that the experiments are monotones? Could you do it also with derived fermions?
I mean, you could do it with complex fermions if you want. And it's just a little bit more complicated, but people have done that.
Well, the reason that I'm asking is because in that case, in some continuous version, you can bosonize it. But not for the marijuana.
Correct. Yeah. I think people have studied that maybe. Yeah. Also, I wouldn't say it's kosher, I would say it's halal. Okay. Okay, where do I go from here? Okay, let's look at, okay. There's an interesting way to interpret the trace of an operator. You can think of it as the sum. You can introduce some orthonormal basis, and it's the sum over that basis of something like this. Okay, we start with the state. This is the definition of the trace, and then you act as the operator, and then you close it. But you can also think of this as sum ij, I left, I right, e to the minus beta h, let's say right, I left, j left, j right. Okay. So here we are taking the overlap or the matrix element of this operator within this maximally entangled state. Diagrammatically, the maximally entangled state I will represent with a short line. This is, okay? And this time evolution with the Hamiltonian I will represent with a long line of length beta. Here, this prepares a state of two systems, and H here takes a state of one system to another.
I runs over is a complete basis.
It's a complete basis. Yes.
I and J are
So from
left
one
and right.
to each of these is I'm summing over J, so this is supposed to be a maximally entangled state in the 2 copies of the system. 2 copies of the SYK system. And this goes from 1 to, I guess, 2 to the n over 2. That's the size of the Hilbert space.
And the Hamiltonian doesn't only on the right, not on the left.
Correct. Right now, I'm writing it as it acts only on the right. Because that's how I would get something like this. If I write this in the energy basis, I can think of the H acting on either one in any way I want. Right? Because if it's an energy basis, it doesn't care about if it acts on this guy or that guy. It's just a number. This picture here, I want to represent as a circle. Okay? There's nothing inside here. Okay? I just have a circle. And the way you should think of this is that I'm starting with this guy here, which I want to represent as a little segment here. Then I evolve with e to the minus beta h for some length beta. And then I'm closing it with this length here. Okay. Another thing you can do, which will be useful for us, that you can write the exponential. You can trotterize it. Okay, you can write this as the limit as epsilon goes to 0 of 1 minus epsilon beta h to the power of 1 minus epsilon. What this amounts to doing is you break up the circle into epsilon beta sized segments, and in each segment you insert 1 minus e times beta times h. So when you're computing, so here there's an average over J, you can expand this, and you'll get terms of the form minus beta to the power of k times trace h to the k. Okay? For various values of k. Now let's go through the process of calculating this quantity for different k's. The first example to consider is just trace h, the case of k equals 1. In this case, the diagram looks something like, here's my circle, and it's somewhere around the circle, I have insertion of 1 Hamiltonian. Okay? This might be a little bit confusing. While the length of the circle is beta, you should think of this as inserting h, the operator h, and then evolving for a time beta using a Hamiltonian which is equal to 0. Okay? Notice that it's trace h, not trace h times e to the minus beta h. Okay? So I just have a circle here. The length around the circle doesn't mean anything, but right now just think of it as a circle with 1 insertion of h. Okay. Well, this h has only a single factor of j, so when I average over j, I'll get 0. Okay, so that was easy. What about trace of h squared?
So is this h or hr? What happens to hr?
Now it doesn't matter, right? Because when I wrote it down here, hr sort of I had to specify where h acts, but
So it's acting to the right.
it's acting to the right in the sense that when I started here,
Yeah.
I evolved in this direction. That's what it signifies. So now if I compute trace h squared, I will draw the same circle, but now I will have 2 copies of h. So one here and one, let's say, here. Okay. Now we can get something which is not so trivial. This thing is this thing comes with there's a coupling here, JI1, capital I1, and here there's a coupling I2. So this thing is equal to the average over the J's, I1 j I2 times the trace of psi p I1 psi p I2. When I average over the j's, I get a delta function setting I1 to be I2. So then, okay, this thing is delta I1, I2. And so here, this thing is I1. And there's a sum over I1 and I2. Because it's in H. H is a sum. And now this is also I1. And then what you can show is using the algebra of the Majorana fermions, psi1 times psi1 is just equal to 1. So you can cancel this set of psi's with this set of psi's. Okay? So this is just going to be some number. And the number, it's not important what the number is, but let me just write it down. Well, this thing is going to be just n choose q. N choose p. Okay. And this thing is going to, well, anyways, there's some factors that it cancels with, blah, 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 and you get some number. Okay, good. The representation of this contraction here, let's draw a line between the two j's. Let's do something a bit more non-trivial. Let's compute trace h to the 4. In this case, you'll have a circle with 4 insertions of h, and there are now more wick contractions, right? You can have this, you can have this, but you can also have this. The first two terms are really just a square of what we found for the one pair of Hamiltonians. So this answer is going to be, let's say, 1 plus 1 from those, plus something that comes from this guy. Maybe I should write this as, this is trace H, 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 H. First two are, so there's this contraction, there's this contraction, and finally, there is this contraction. Okay? That corresponds to this case. So this means that this term, when they intersect, they will look something like this. Some I, j, but this is a different j. Okay? Trace psi I, psi j, psi I, psi j. What we want to do is we want to take this psi I through this psi j in order to cancel it with this psi I. Okay? If you take this through, what you get is, well, this thing is going to be psi I, psi j times minus 1 to the power of the number of intersections between the fermions. Okay? So this thing has, each of these guys has p of the n fermions. When you take this guy, when you take it across the other set, you pick up a minus 1 depending on how many fermions they share. Okay? But then, so after you do this, then you can cancel this psi I with this psi I and this psi j with this psi j. And all you're left with is just a sum over this intersection number. Ij minus 1 I intersection j. Okay, so how do you evaluate this? It turns out that the statistics of these minus 1s just follows a Poisson distribution. And it's something that you can derive in the following way. You can say, suppose that the intersection is equal to k, so they share k fermions. Then what is the probability that they share k fermions? Well, you choose from the p fermions, you choose k. You multiply by the you multiply by the combinatorics of the remaining fermions not containing those k fermions. So that's n minus p, p minus k, divided by all possible combinations of fermions. That's n choose p, and then you can show in the large n limit that this is just 1 over k factorial p squared over n to the k e to the minus p squared over n. So this is just Poisson, which means that on average, so when you sum over these i's and j's, the average of this quantity is just going to be e to the minus 2 p squared over n, which is e to the minus lambda, which henceforth will be defined as q, not p. Okay. So now we have a general prescription for computing these diagrams, for computing trace h to the k. So trace h to the k. So you have a, so then over here we have this thing is 1 plus 1 plus q. That's the answer to trace h to the 4 times an overall constant, which I'm not going to keep track of. So trace h to the k, you have to put, k insertions of the Hamiltonian. And then you draw all possible chords, chord diagrams, and so on. And then you say that, well, all you need to do is count the factors of q, the number of intersections, and that assigns a number to each diagram. So the total answer for this is it's a sum over chord diagrams times over q to the intersections. Okay. Okay. Now, here we represented the trace in terms of an overlap of boundary states. We want to do something similar here. We want to represent these diagrams, these chord diagrams, in terms of overlaps of bulk states. Okay? And the way to do it is the following. So the first step is to define the so-called zero chord state. Okay, so I'm going to label as that, 0. The zero chord state is the state where you haven't acted with the with any factors of the Hamiltonian. Okay? That means, from this perspective, that it's like the maximally entangled state of two sides. Right? So I drew something like this before. This is like the zero chord state. And this picture will become more clear in a second. Suppose we consider the state H acting on 0. Okay? This is the standard, this is the boundary Hamiltonian H. This thing is equal to, we would draw this the same line, but now with one insertion of the Hamiltonian. Okay? Okay. This thing, I want to think of it in terms of the bulk as I want to extend the chord into the bulk. Okay? Hence, what this defines for me is a chord state with one chord. Okay? If you compute now 0H0, we know from before that we should get 0. This thing is like taking the overlap, it's like drawing a circle like this and putting a single dangling chord in this fashion. The reason why this is 0, the way you should think about it, is that there's nothing for the chord to end on. This is a statement that we needed an even number of j's to get a non-trivial answer. Okay, so then let's keep going.
Are there any parameters associated with this chord, its direction?
No. With a simple model, nothing. Yeah.
Nothing.
Yeah, yeah. I think when you have, if you consider like the charged version, you would have, there would be an arrow. This is my guess. I haven't actually done that, but it seems natural. Suppose now you act with h squared. So h on O. Again, just like what we did in the part that I erased, I'm always going to go to the right. Okay? So this is like, so we had one chord, that's h on 0. Now I'm going to insert another h. And there are two things that can happen. One thing is that the second h, well, now you create a chord here. One thing that can happen is that the chord contracts with the old chord. Another thing that can happen is that you get two chords. So you went from the state 1, so this is h on 1, and you ended up with a state here with no dangling chords. So this thing is proportional to the 0 state plus the 2 state. Okay? And let's do one more example. The h to the 3 on 0.
So this is an effective definition of the 2 state. Right?
Yes, yes.
Would you have to know the coefficient?
Yes, yes. I'll come back to that. The coefficient of this.
Yeah.
Let's say for now that we've normalized chords to give you 1. Okay?
Can two chords be emitted at the same point? Doesn't matter if they are. Is there some symmetrization between them? Nothing.
No.
No.
No. But you can't have. But each point only emits one chord.
Okay, so you can't emit from one point.
No, because each point corresponds to h. Okay. But also, this distance doesn't mean anything in between. Okay, so this thing can be thought of as h acting on the 2 state. Actually, no, let me not say that yet. Because it's not true. This thing is now, so we're just acting h on what we have here. Here, what can happen is that you have this guy with an extra chord, plus h here with 3 chords, plus this guy, plus this guy. Now something interesting happened. We generated a diagram where chords start to intersect. This thing here is the 1 state. This thing here is the 3 state. This thing here is the 1 state again. And this thing here is also the 1 state, but with an intersection. What did we learn about intersections? That they give you factors of q. So this means that this thing comes with a factor of q. Now, if we just focus on, so this is h to the power 3 acting on 0. Let me specialize and only look at h acting on the state 2. Acting on the state 2 means this term is not there. All I have is this. I have these 3 contributions. So state 2 is defined as this. Okay. So let me actually write it. Okay. This answer is well, it's clear what it is. It's 3 plus 1 plus q times 1. And in fact, in general, where you have, if you act with h on a state of n chords, you get the following formula. With a state of n chords, meaning it, yeah, so that's clear. It's equal to n plus 1 plus 1 plus q dot 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 plus q to the n minus 1 times n minus 1. Okay? This object here you'll recognize as 1 minus q to the n over 1 minus q. Okay. Now what I want to do, so far I've been thinking about the H as something that acts on the boundary. But nothing stops me from reinterpreting this as saying that there's an H in the bulk that creates and annihilates chords. Let me define that as T. There's a bulk matrix T for transfer matrix, which has the following form. Alpha dagger plus alpha times 1 minus q to the n hat over 1 minus q, where alpha is just a shift operator. So it's like the creation operator, but without the square root n. Or to write it explicitly, it's 1 over square root n hat times a dagger, the standard a dagger. Okay? That's what alpha dagger is.
Standard 8 dagger of what? Of fermion?
No, on this basis, n. It just creates and annihilates chords. It's just a level system.
Yeah, okay.
Yeah. But the level keeps track of the number of chords. Okay? This transfer, the reason why I didn't call this a Hamiltonian, rather the reason why the original authors, Vercruysse and friends, didn't call this a Hamiltonian, is because it's not Hermitian. It's just a transfer matrix for now. And we'll come back to that in a second. You see here, n is an operator, by the way.
Sir,
Yes?
alpha is 8 dagger over what? Over the square root.
Of n hat. So it's like the creation operator, just without the square root n that comes along usually.
Right.
So it's just a shift operator. This thing increases n by 1, alpha here decreases n by 1. And this is just some factor, but it depends on the n, it has an n operator here. So when I act n hat on state n, I get back n. Okay. Just alpha, it's just a dagger a. Okay. Now what this transfer matrix does for me is that it generates the following bulk evolution. I started with here, and then as I act with T, I generate this kind of evolution. Okay? Here I'm imagining that I'm computing something like e to the minus beta t, where I start with the 0 state. Right here, I started with a 0 state, and then I evolve for some like beta, and then I end again with a 0 state. Okay. All right. Let's fix the non-hermiticity of this operator. The reason why it's not Hermitian is because these states, these chord states, are not normalized correctly. So let's normalize them. Because we've written T in a basis which is not normalized. That's why it's not Hermitian. So let's compute the overlap of n, m. Okay? This thing, just by the previous argument, so here I have n states, and then I have at the top m states. When I take the overlap between n and m, I do not allow chords in n to contract with one another. They're allowed only to contract with the states in the broth. Because otherwise, I would not have called this thing an n state. But then this means that this thing has to be proportional to delta nm. Okay? So it is diagonal. That's good. Times nn. But there's a combinatoric factor. What is a combinatoric factor? So you take the first one and you sum over all possible ways of contracting these chords. That would generate intersections. So when you take the first one and you combine with this guy or this guy or this guy or this guy, you would get 1 minus q to the n over 1 minus q. That's for the first chord. And for the second chord, 1 minus q n minus 1 over 1 minus q, dot, 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 dot. So then the answer, eventually, is going to be the so-called q Pockhammer symbol over 1 minus q to the n. This is the q Pockhammer. Said differently, this is what is, well, this is often called the q-deformed factorial. You can convince yourself when the limit as q goes to 1, this top factor here goes to n factorial. Yeah, and in fact, so this expression here, this thing is called the q-deformed integer. When q goes to 1, you get n. Yeah, it seems like for quantum gravity you need something like this. You need to q-deform everything. So when you're teaching your kids how to count, you should start with the q numbers first. Okay, to get them ready. Okay, all right. So so we can then define the bulk Hermitian Hamiltonian as simply the matrix elements of it, as simply the matrix elements of the transfer matrix but after normalizing the states. Okay? And these overlaps are just what I wrote down here. If you do this, this modifies the transfer matrix to the following formula. There's a minus 1 over square root lambda, not very important, times alpha, square root 1 minus q to the n hat over 1 minus q, plus square root 1 minus q to the n hat over 1 minus q, times alpha dagger. Okay? Which is very Hermitian. Something interesting about this, about these two terms here, is that this object here is what you might have called the q-deformed lowering operator. And this guy here is the q-deformed raising operator. If you take their commutator, you do not get 1. But if you take their q commutator, or in the literature it's called q-mutator, I'm serious, they actually call that. Where you insert a factor of q here, then you get 1. Okay? This is often called the q-deformed Heisenberg algebra.
So q is e to the minus lambda?
E to the minus lambda, yes. This has showed up in many contexts, most famously in integrability, where, but I think in that case the q was a root of unity, or, yeah, maybe, remember something like that. Also, because this is just a plus a dagger, this is what you might also call the position operator, the q-deformed position operator. If you define, so this is just an aside. If you define a Hamiltonian, a harmonic oscillator Hamiltonian, it's called HQ, to be a dagger a q, something like this, then you get plus the Hermitian conjugate. Then you, it's also you get levels, obviously, because these are integers. But you end up with an accumulation point. There's a maximum energy, which, so E max goes as some number, I'm not going to try to reproduce it, divided by 1 minus q. You get the standard harmonic oscillator back as you take q to 1. But then this accumulation point goes to infinity. So it's no longer an accumulation point. Okay. Now, let's make contact with JT gravity. So this theory is defined for any number of chords, a small number of chords or a large number of chords. To make contact with JT, we should take a large number of chords.
This was part of the calculation of the race of e to the beta a. So what is the final result that you get? You add this h to the k as part of this. So you have a closed formula for that?
All the eigenfunctions are known. So in principle, yes, you have you have a closed form expression for that. But it's a bit unwieldy. But in certain limits, you can say whatever you want about it. Yeah, I'll say a few words.
So can you say what's the each bulk and each what's the feature bulk boundary?
I was just saying, so here, when I was doing this thing now satisfies, no, it doesn't satisfy this condition. But, so, what was I saying? I was saying that you can think of the procedure of adding h's on the boundary. You can think of that as a procedure of adding chords in the bulk. So you can think of it as a purely bulk operation, okay? So you have a bulk Hamiltonian, which controls how the number of chords changes as a function of time.
Well, what is the geometrical meaning of the chord?
Yeah. So to make contact with JT, let's define L to be n times lambda. Okay? Let's assume for now that lambda is small.
Define what's n?
And that appears here. Okay. Okay. As in, let's think about this system classically. Okay. Like, if you want to think about it classically, what you should write is well, I'm going to work in the limit where lambda is small, so I can think of L as a continuous parameter. I can define K.
You're thinking of a particular state n?
Yes.
And we are looking for what corresponds to that? That's how you pick your n?
Yes. Or I'm going to, more carefully, I'm going to pick a class of states for which n is very large. Okay, that's what I'm going to do. The Hamiltonian, just in terms of these variables, now what I'm going to write doesn't really assume anything except that that K is a derivative of L, that the derivative of L makes sense. H, bulk, is 1 over minus square root lambda times 1 minus q of e to the I lambda k times square root of 1 minus e to the minus L plus square root 1 minus e to the minus L e to the minus I lambda k. These were the shift operators. Okay? The eigenstates of this Hamiltonian are determined in the L goes to infinity limit. The eigenstates from L goes to infinity. These are scattering states. And so E is equal to minus 2 cosine lambda k. So you drop L divided by square root lambda of 1 minus q. Eigenstates are thus labeled by lambda k. Let me define lambda k. Well, sorry. Let me define lambda k at theta. And the energy goes from well, minus 2 to plus 2 divided by this factor. Let's go to flow energy.
If you take q to 1, what would that give?
If I take q to 1?
Yes, where would that
Yeah.
give us? What would?
It would be let me give a quick answer and then talk about it more later. So you mean what is, well, the Hamiltonian is just going to be the X operator of the harmonic oscillator. Okay? There's a question about what is the bulk dual of that. Maybe I can say a word or two later. So let's look at the low energy limit. And also take lambda goes to 0. And we take L goes to infinity. Okay, now I'm focusing on class of states where L is very large. If you do that and you expand this expression, you get that H is equal to minus 2 over lambda, some ground state energy, plus lambda times k squared plus, oh, sorry. I forgot an important thing. We're taking the limit lambda goes to 0, L goes to infinity, but e to the minus L over lambda squared, define it as e to the minus L tilde, is fixed. This is the so-called triple scaling limit. If you do this, then the Hamiltonian you get is the following.
Hamiltonian H bulk.
H bulk, thank you. Okay? K is a conjugate momentum of L. So this is really L dot squared. Plus e to the, well, L tilde dot squared e to the L tilde. This is the JT Hamiltonian that we talked about before. So we cover the Hamiltonian of JT gravity. And what was important, so now we have a nice interpretation for N and L. This is somehow the length in the bulk, but not just any length. It was the length of a geodesic. If you recall, we were talking about a geodesic. So it's a physical thing. In this theory, in the case where lambda is not small, what it says is that it measures length in units of lambda. Okay. Okay.
So this probably a question, but is this supposed to be the Wheeler-DeWitt Hamiltonian? And shouldn't this H annihilate all states in the bulk?
Well,
is it some boundary Hamiltonian?
Yeah. It
Some
matches onto the
boundary
ADM Hamiltonian, yes.
Okay.
But let me see, does the ADM Hamiltonian kill?
Well, the bulk Hamiltonians usually kill.
That's right. But I guess what I'm saying, what you're finding here is that you end up with a bulk description that is already in physical degrees of freedom, it's like gauge fixed, if you will. Which kind of makes sense. If you're starting from the boundary, surely you should only get things that don't depend on the bulk diffeomorphisms into a gauge or whatever. Yeah.
L tilde is the normalized length?
L tilde is the normalized length.
And L, the way you find it?
L, that's like the bare length.
So lambda also serves as a unit
Yeah. It's what it does is that it. I didn't talk about this before, but even in JT gravity, you subtract to normalize the length. You subtract like log of something that goes as phi h, roughly speaking. No, phi boundary. Phi boundary, where this thing diverges. In this case, it's like we're normalizing the length by log of lambda.
Really good parameter J.
Sorry?
Really good parameter J of the
Yeah.
DSYK.
Good. I set J to 1 at some point, secretly. But ultimately, this length should be measured in units of 1 over J. I think that's the right place to put J. This Hamiltonian, well, not this one, the full Hamiltonian, you can find all of its eigenfunctions, diagonalize it, do whatever you want with it. And you can express the energy eigenstates in the n basis. So I'm labeling energy eigenstates by theta, and it's equal to some measure, mu, well, so some number, some function of theta. It's a complicated function involving Q Park hammers, etc. Times a Q deformed Park hammer, Q deformed Hermite polynomial. Divided by the square root of the Park hammer. So again, it's like you're starting with a harmonic oscillator and you're just deforming, you're Q deforming it. Okay?
Not in the low energy limit.
This is general now. This is general. Yeah, this is general.
That should be identified with the block in the book.
This is just some, this is the wave function of, well, yeah, it's an energy wave function in the n basis. It's a,
Let's say in the bulk we have black holes. Is one of these states a black hole, or are there many of these states black holes?
yeah,
Or
I don't know.
What's the correlation between the scalar fields and the geometry?
Excellent,
that's what we
excellent
asked
research
about.
question. All I can say is that for when L is very large, these are black holes. When L is not large, the question is, how is there any semblance of geometry? Okay? We don't know. Right now, it's just some discrete graph. Yeah.
Well, you kind of lose the geometry because there's no dynamics of the bulk. How do you see geometry? It's over the boundary.
No, there is a way to see geometry, which is to compute correlation functions. Okay? But before I do that, I just want to make the following. I think it's an important point. You can ask the question, okay, SYK, or yeah, double scale SYK, it has its own Hamiltonian and it has a density of states. Where does the SYK density of states originate from the bulk? Okay? Is it just the density of states from diagonalizing this Hamiltonian? The answer is no. And let me explain it. So e to the minus theta HSYK. From the bulk perspective, this is 0 e to the minus theta HB for bulk, 0. Let's write this in terms of the energy basis. It's going to be integral d theta 0 theta squared times e to the minus beta e of theta. This thing here is what I call mu. Mu. And this is the thing that gives you the density of states. It comes from the wave function in the chord basis. Yeah. Okay. And mu theta, if you plot it, looks something like this. And the limit when lambda goes to 0, this peak is very, very high. It's centered at about 0. This is mu, that's a mu of energy. It's a function of energy, and this is energy. This is 0, this is minus 2 over whatever lambda, square root lambda 1 minus q, and here's the plus of that.
So near the center, what is the energy
yeah.
dependence?
So near the center, this thing, brace yourself. No? The Hamiltonian, just the X operator of the harmonic oscillator. That's all it is.
I'm confused. The Hamiltonian, here you say the Hamiltonian is the X coordinate, but in this formula, theta is the X coordinate of the harmonic oscillator.
Yes. It becomes, no, not quite. Maybe I should put here d cosine theta. Because energy goes as minus times cosine theta. Yeah. And it goes from, and it's important that it's normalized by 1 over lambda. In this regime, effectively what's happening is you can take lambda to 0. So energy then goes from minus infinity to infinity. And then it's consistent with the fact that X has a spectrum which goes from minus infinity to infinity. But yeah. Okay. The final thing, well, I'm over, I guess, right?
Yes, but we are not.
Okay.
We're at the beginning of the day, not the end of the
Okay,
day, like
okay.
yesterday.
Okay.
Ahmed, just a quick question. You wrote an overlap of an energy eigenstate and light basis above n theta. Do you reproduce the JT gravity answer in some limit?
Yes, yes, yes. Everything you can reproduce.
What is the joint interpretation of the theta and the n state?
These are like fixed energy states in JT gravity.
The theta.
Well, the energy is cosine theta. So that's how they're related.
And what is the n? The
Oh.
n state?
Oh, and are fixed length states. So in JT gravity, you can choose a state which has fixed length in the bulk, or you can choose a state which has fixed energy at infinity. You can't specify those two together because L does not commute with H. Yeah.
So, state like this is Schwarzian state if you only find geometry is an n-state or from H?
You're asking about how do you get the Schwarzian from this?
Okay, forget about the code, just what you said about JP. So what do you find a state for different geometry? Is it like an L state or not?
Yeah, that's it depends on where you are. It depends on the size of L. I think for now only large length states. Or let me get to the next part about correlation functions, and that should address your question. Ultimately, if you have a state of fixed L, at least on that slice, it is definitely fixed L but large, it is definitely a geometric state on that slice. I don't know about what it evolves to and things like that. Okay, so correlation functions. First let's define, so correlation functions of what? Let's define operators M that come with their own disorder parameter. Okay, so these are J tilde from I1 all the way to I P prime times psi I1 all the way to psi I P prime. Okay, where you're summing over all these i's. Also from 1 to capital N. Okay. So these are the operators whose correlation functions we're going to study. So now the rules are the same. So here's the circle. Suppose I have a state. Let's compute the expectation or the 2-point function of M in a fixed n state. Okay? What I mean when I write this equation or this formula, this expression, is that I have a state of n chords. I insert n here and an n here, and then I close it with n chords. That's what I mean by this expression. Now we average over J tilde. This means I have to contract the two m's together. Then I have this guy. Okay? But when you do this, you're going to get these they're going to intersect the. Let me say these are the operator chords and these are the Hamiltonian chords. It's going to intersect n Hamiltonian chords. And again, just like before, there's a penalty factor for intersections. And the penalty factor here is going to be e to the minus 2p times p prime over n. P was the number of fermions involved in the Hamiltonian. P prime is the number of fermions in the operator. So this is the answer. But it's interesting to, you can re-express this and, oh, sorry, no, this is not the answer. Times n. Okay? For each Hamiltonian coordinate intersects, it picks up a factor. There's a nice way to re-express this. Imagine, so multiply by p, divide by p. This thing then becomes e to the minus lambda times n times p prime over p. If you define this thing as the length, and define this thing as the dimension of the operator, well, this thing looks like e to the minus delta times n. So at least from this correlation function's perspective, it looks like you have a nice geometry here. Okay? But upon sort of further investigation, at least I learned from Henry Lin and friends that there are some examples where you don't focus near low energy, you're focusing at some higher energy, or let's say you don't focus in the regime when beta j is large, okay, so not this. You find that the lengths don't make sense as a Riemannian geometry. Yeah. I seem to find something similar when I focus on this region here. I got an answer which didn't make sense from a Riemannian geometry perspective, but then I got an email a few days later from somebody who claimed to have found a metric that reproduced that answer. But I haven't checked it yet. So hold your breath. Anyways, yeah. So I don't know. I'm really excited about this development because it's like what we always wanted, right? Like gravity comes from some discrete, more fundamental structure, but not just that. Like the usual, it does it it seemingly does it in a smart way, because usually if you say you start with some theory, some quantum field theory, and then you turn on some Lorentz invariance breaking deformations, it's something that would mimic, say that the theory comes from some discrete theory in the UV. Those deformations are relevant usually. So they come in and they destroy your theory in the IR. This is usually the complaint against loop quantum gravity, right? That they start with some discrete thing and so on. But that doesn't happen here. Here, in principle, this theory in the UV, like suppose you work in the 1 over lambda the lambda expansion, okay? Where you start with lambda expansion at very low temperatures. Then you expect that to Einstein gravity there are going to be some deformations, which in principle should break, add some discrete structure. You might naively have thought that it would do so in a way that would become important in the IR, but somehow it knows how to do it in a way that actually goes to 0 in the IR. So I think there's still a lot to learn about this, and yeah, let me end there. Yeah, meet.
There is a gap for me between the previous lecture and this one. Is there a precise statement of the duality between the previous picture and this one?
Well, the fact that at the very end we got JT gravity back, you could redo all of those calculations, but in this model. But other than that, there is no direct connection between the two subjects. Sorry?
There's no bath theory.
There's no bath theory, for example, but you can imagine you can cook up a way of coupling into a bath.
So this is just at the stage of the duality between pure JT gravity and some quantum mechanics.
Correct.
Beyond that, nothing is known as of yet.
Well. So let me say the following things. So something that has been analyzed to death. Well, not death yet. So is Z, the partition function of SYK, okay, at some temperature beta, I guess that doesn't matter, and Z of JT gravity, okay? Those have been compared at various levels. We know that they're not exactly equal, but they're equal in some regimes in a controlled fashion, and it looks really nice. What this story is telling you is that you now can make an identification between the Hilbert space of SYK, or rather of double-scaled SYK, equals, no. Well, no, maybe that's too quick. Okay, let me put a squiggly line here. With the Hilbert space of the coordinates, okay, which you can think of as a bulk Hilbert space. So now, we don't just have a duality between partition functions. We have a duality between Hilbert spaces. And operators, yes. Yes, yes, yes.
But low energy limit agrees with Jim.
Correct.
But we know that it was not
So the Hilbert space of the code is a well-defined theory.
Yes.
right, but it's not JT gravity beyond the low energy.
Correct, correct, correct.
It's string theory.
Maybe. Or don't shoot me, loop quantum gravity. I'm actually pretty serious about that. Like they actually work with these Q.
If it's consistent, it's
yeah.
also string theory.
Oh, okay, that's the spirit. Yeah.
But this identification that you just mentioned, the quantity trace, the integral of theta, I can tell that this factor is like the degeneracy or something like that?
Yes, yes, yes.
So then, what do you actually mean when you equate the input spaces?
I just mean that for any, so for example, let's consider that you can list the, you can have a one-to-one map between states in the SYK and states in the bulk. For example, the sum over this left and right. If you take two SYKs and you sum over the energy from over all the spectrum, this is equal to the zero chord state, and so on and so forth.
As you said at the beginning, the gravity theory is also on the back, on the boundary, not nothing in the back.
I mean, there is higher topology in the bulk, for example.
But there are also other degrees of massive degrees of freedom.
Ah, that too as well. Exactly, exactly.
And, you don't see that here.
That's right. That's right. Well, you could add them, but like for example, you can consider the theory with one particle, two particles, three particles, and you can also write down the Hilbert space of those. The Hilbert space is these special particles where they each come with their own J. The Hilbert space is just a direct sum of having 1, 2, 3, all the way up to infinity number of particles.
How far is the entropy? Can you compare the entropy of the black holes in the JT gravity to some entropy of the SYK or whatever?
Yes, yes, you can. Yeah. In the low energy limit.
Okay, well,
one final question.
What happens to the high energy limit? Like, is it something like some force subspace in low energy limit? If you put too much energy, it breaks this.
Depends what you mean by high energy limit. Do you mean this region or do you mean this region?
No, you took some low energy limit lambda.
Yeah.
So this duality is exact there.
Between JT?
JT and this one.
Yes, but with corrections that go as 1 over the energy. Let's think of it like that. And lambda.
let's thank Ahmed again for